Welcome! In this video, we will discuss problem 6.26 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now, this problem is the same as 6.28 as it appears in the second edition of the same book. Now, this problem states the following. It looks like a very long text, but it's not that much. It says, by appropriate modification of the hydrogen formula, determine the hyperfine splitting in the ground state of a muonic hydrogen, which is a muon instead of the electron. Then we have positronium, that's part B, which has a positron instead of the electron, instead of the proton. And finally, we have muonium, which is an anti-muon instead of the proton. So it's basically different types of hydrogen, right? So in hydrogen, we have the nuclear part, which is one proton, but let's call it N, right? The nuclear part. And we have the orbital part, which is usually the electron. I'll call it just O because we're going to be changing it in the different parts of this problem. So how did we find this hyperfine splitting? Well, the formula that we found previously was that in the most general terms, the hyperfine splitting, the energy due to it, of course, this is the G factor times E squared divided by 3 pi, the mass of the proton, mass of the electron, A cubed, and then SP, SE. So this is what we found. And what is important to note is that, well, first of all, we saw that the energy due to this, right, the energy due to this is 5.88 times 10 to the minus 6 electron volts, right? So this leads to a splitting of this amount. Now, we want to generalize this because this is, of course, for hydrogen. Now, let's take a look at this thing. So if instead of hydrogen, we had something else, so basically we had something with a different G factor. I'm just going to call it GI, where I can be for, I don't know, for the electron, for the proton, for muon, for whatever. It's something else. The charge will still be E squared because in every situation, in muons, with the antiproton, I think it is, and the antimuon, all of them have the same charge. So that's not going to change in any of these situations. Then we have 3 pi. And then instead of the mass of the proton, we have the mass of the part in the nucleus times the mass in the orbital, right? Of course, in the case of hydrogen, the nucleus is one proton, the orbit is one electron, and we get the same as before. And then we have this modified Bohr radius, because the Bohr radius, of course, depends on the fact that you have the electron and the proton. But if you have now different things, you know, the radius is going to be different. Okay, so what now? Well, now we want to actually begin. So in part A, we are dealing with, so part A is muonic hydrogen, which means that we have a muon instead of the electron. So this right here will be a muon. And what does that mean? The muon has the same charge as the electron and the same G factor. However, the G factor is not relevant here because this G factor is for the one in the nucleus, not for the one orbiting. Okay, so that's why we don't need to worry about that. The electron one is already considered in here and it doesn't change, right? So no worries. And then we know that the muon has 207 times the mass of the electron. Okay, and something important to note is that we shouldn't, don't forget to use the reduced mass, okay? So how do we do this? We basically want to take this thing once again. And by the way, I forgot to write this down, but the spins won't change, right? The spin of all of these particles are 1/2, so this never changes. This will always be the same, even though I just called it SP, perhaps I should call it this would be nucleus and this would be orbit. But all of our particles have spin 1/2, so nothing changes there really. Okay, So now let's go for the energy in the case of the muon. So this is of course hyperfine. So let's see, now of course mu naught doesn't change at all, G doesn't change because the proton is still the particle in the nucleus, E doesn't change, we have the same charges, 3 pi. Now the mass of the nucleus doesn't change either, but the mass in the orbit does. And now this is where we have a few choices. What we could do is just write this as mass of the muon and times our new Bohr radius and calculate all of these quantities and, get our result. But that is annoying. So we already know the numerical result of this. So if we write m mu, right, the mass of the muon in terms of the mass of the electron, and we write this new Bohr radius in terms of the old Bohr radius, right, the normal one, then we end up with the same expression, and we already know what its numerical value is. So what we now want to do is go from these mu and ai to, the same expression that we had before. That's going to be our goal throughout this problem, actually, in every single case. So we know that the mass of the muon is 207 times the mass of the electron. So that means that we can, instead of writing this right there, we write it as mass of the electron, and here we just divide by 207, right? I separate this so that it becomes very clear that we end up with the same thing here. Then we need to find this Bohr radius. Now that is going to be a little bit more difficult, but not too much. So what we'll do is make the ratio between the normal Bohr radius, right, and this modified that is due to the muon. So actually maybe let's label this mu because it is due to the muon. Now, how does the Bohr radius depend on mass? Well, let's go back to the formula so that you can see it. So the Bohr radius that we saw for hydrogen is 4 pi epsilon 0 h bar squared divided by me squared. Now notice that none of these quantities change when we go to a muon or any of the other quantities, a positron or anything like that. All of those are constants, and this is the charge, which all of our particles have the same. So for that reason, we have to consider that A just goes as 1 over m. That's what matters, right? Everything else cancels out. So if A goes as 1 over m, then here we got the reduced mass, and here we got the mass that we had previously. In this case, it is the mass of the electron, of course. Okay, so what now? So now, well, we need to write what the reduced mass is. So we have 1 over the mass of the electron and the reduced mass. So the reduced mass is the product of the mass of the muon and the mass of the proton. So, and divided by the sum of those masses. So what is this? Well, we know that the muon has a mass of 207 times the mass of the electron. So we get 207 MEMP divided by P plus 207 ME. So here we can cancel out these masses and multiply by 1 over MP so that we have a bit of a simpler expression. So 207 divided by 1 plus 207 ME divided by MP. Okay, and what is this? Let's just plug it into our calculator. So that is 207 times the mass of the electron, which is 9.1 exponent minus 31, divided by mass of the proton, which is 1.67 exponent minus 27, which gives us 0.11. We add 1, and then we raise this to the minus 1. We multiply by 207, and we end up with 186. 0.02, but that's good enough. If you want to use more decimals, go ahead. So this means that A is equal to 186 A mu. So that means that if we want to write our expression in terms of A, we can use that A mu is A over 186. So plugging this in right here, right, instead of this A mu, we get A, and since this is divided by 186, we are basically multiplying here 186 cubed, of course, since this thing was cubed. And there we go, look at this. So now we know what this is. This right there is simply the exact same as before. Again, because all our particles have the same spin. So we may as well write this as sp.se just as before, and we end up with this thing being 5.88 times 10 to the minus 6 electron volts times 186 cubed divided by 207. Now, what does this give us? This is 186 cubed divided by 207 times 5.88 minus 6 exponent. So this is 0.18, I guess you can go 18.3 electron volts, right? You could go for some more decimals if you want. It depends on what you're doing. I'm simply showing you the procedure. So if you want to use more decimals than me, go ahead. So this is the hyperfine splitting in the case of muonium. Now let's go for the next case. So the next case, so let me get rid of all these lines. The next case, B, is positronium, which is, so positronium, this is a positron which has the same mass and same G factor as the electron, but opposite charge, and it is substituted for the proton. So basically, instead of having a proton, right, in the center, our nucleus element is now positronium, which has the same charge as the proton, but a different G factor, right? It has the same G factor as the electron. And keep in mind, the G factor in our formula is due to the particle in the nucleus, which now is a positron. So of course, the G has now changed. Okay, so we will have different mass and also different G factor. Okay, so let's go to our formula. So just as a reminder, right, we want to plug everything in there. Again, our spins will not really change, and that's going to be our constant throughout the problem, actually. So the energy for now positronium, due to hyperfine splitting, this will be now mu0, that hasn't changed. We have 3 pi. Now G does change. Now we have G due to the positronium. Then we have, or positron, sorry, positronium is the entire thing. Then we have the mass of the element in the nucleus, which is a positron, which has the same mass as the electron. Then we have the mass of the element that is orbiting it, or the particle, which is an electron. And then we have our modified Bohr radius for our positron. Okay, and of course, now this product, which is the same as before, I'm just going to write it as sp.e. It's the same as before. Okay, so we need to now find our new G. So we know that the G factor for the proton is 5.59, while the G factor for the electron, and thus for the positron, is 2. So again, we want an expression that looks exactly like this because we already know the numerical value. So for that reason, let's take the ratio between these two. It doesn't matter which you divide by which, you can always change it later. So let's say GE divided by G proton. Now, again, I don't know if this is the correct way. We'll see soon enough. So here we get 2 divided by 5.59. And of course, just to make this very clear, since the G factor of the positron is the same as for the electron, we can just label it GE. So from here, we can see that GE is going to be 2 divided by 5.59 times the G factor of the proton, which we simply called G previously, so we can go back to that notation if we want. Just going back to that notation, we found that part. Now we need to find how to turn the mass of the electron into mass of the proton, which is going to be the same. We know that the mass of the electron, right, let's do mass of the electron divided by mass of the proton. So this is 9.1 times 10 to the minus 31 kilograms, but the kilograms will of course cancel out, but I guess I can write them. And then we have 1 point, maybe let's use commas, 67 times 10 to the minus 27 kilograms. So from here we multiply through and we get that the mass of the electron is, now let's do this product, it's about 1,000 times, right? 9.1 e to the minus 31, 1.67 e to the minus 27, I misclicked, 9.1 divided by 1.67 exponent minus 27. So we get, yeah, so 5.5, actually 5.45 times 10 to the minus 4 mass of the proton. So that is what we can now plug in there. And finally, we need to find the modified Bohr radius. Exactly the same as before. What did we do before? Before we said, all right, let's do the ratio between A and the reduced this new A that is due to the reduced mass. So here in A, once again, our dependence is like 1 over m. So the mass of this case is in the denominator and the mass of this case is in the numerator. So this means that here we get the reduced mass, so m reduced divided by m of the normal one from the electron. So here we get 1 over mass of the electron times the reduced mass, which is the product of the masses divided by the sum of the masses. Here the masses are mass of the electron, which is orbiting, times mass of the positron, which is the same, which is in the nucleus. And then we have divided by the sum of those two, so 2me. Now we got me squared, so this is simply 1/2, which means that A is equal to 1/2 of a mu, but a mu in this case, I guess I should have called a mu something else, rather of the positron case, but call it whatever you want. So from here we find that a positron is twice A. So now we have everything that we need. So we can just go back here, plug everything in. So we get mu naught, and instead of GE, we write 2 divided by 5,59 G. So I'm going to write G here, and I'll write this 2 divided by 5,59 here to the side. Now this thing doesn't change. And then we divide by 3 pi. And instead of mass of the electron here, we write it as this thing right there, right? 5.45 times 10 to the minus 4 mass of the proton. So we write mass of proton here, mass of the electron, and let's write somewhere over here, 1 over 5,45 times 10 to the minus 4. And finally, instead of A, we write 2A, right? So we get A cubed and 1 over 2 cubed. So now we simply plug everything in. This thing right here is just before 5.88. So this is 5.88 times 10 to the minus 6 electron volts, right? This is the way where we save ourselves the most trouble. So 5.88 exponent minus 6 times 2 divided by 5.59. Then we divide by 8 and then divide by 5.45 exponent minus 4, which gives us about 4.825 times 10 to the minus 4 electron volts. So in the final case, so let's go C. Now, what is this case? So part C, this says, so let's get rid of these lines again. Part C says muonium, in which an anti-muon, which is the same mass and same G factor as the muon, muon has the same G factor as the electron, as we saw before, right? Muon has the same charge and G factor as the electron. It substitutes for the proton. So once again, we are substituting for the nucleus particle. So that's it. So now let's go back to this. So let's see. we have E, now we are in the, I don't know, anti-muon. I'm going to write it like that, but again, it's simply notation, it doesn't matter, hyperfine. Here we get mu naught, and now G, due to the anti-muon, right? It is in the center, so this time we have to consider it. But G for the anti-muon is the same as for the electron, which is the same as for the positron. So that means that the calculation that we did before is still valid. So this thing right here is simply 2 divided by 5,59 G. Okay, and then we have E squared, right? The charge hasn't changed. It is the same charge as the proton. Now, don't get confused because it says, oh, same opposite charge to the electron. So you might think, oh, we need to change charges. But no. We're talking about the same as the nucleus, so which is the proton, which is what matters. Then we have mass of the nucleus element, which is mass of this anti-muon, which is, of course, the same mass as the muon, times mass of the electron that is orbiting it, and then this new part of the muon. Okay, the new radius orbit. And of course, this sp.se, which will not change. Once again, same spin, all cool. So the first step is to determine what, any of these quantities, right? Let's begin with maybe the mass of the anti-muon. We want to write it in terms of the mass of the proton so that we can then turn this expression into what we have already solved for before, right? This amount that we already know what it is. So let's see. The mass of the anti-muon we know is the same as the mass of the muon, which we know is 207 times the mass of the electron. So let's now take a ratio between the mass of the muon and the mass of the proton. This is 207 times the mass of the electron divided by the mass of the proton, of course. And let's actually, take these numbers. So I'm going to numerically calculate that. So that is, I think we did it before, but it's okay. I'll do it again. Exponent minus 31 divided by 1.67 exponent minus 27 times 207. So this is 0,113 basically. So the mass of the anti-muon or the muon is 0.113 times the mass of the proton. So that is what we care about. That is what we will now plug in here, right? So we get mu 0 G. I'm going to take my constants to the side as I like to do, or basically the numbers that we have now found. So I will have 2 divided by 5,59 times 1 divided by 0,113. And down here we have 3 pi mass of the proton. So there we go. The mass of the anti-muon now changed into 0.113 times the mass of the proton. The mass of the electron remains the same. We haven't done anything to the electron. And now we need to find the modified Bohr radius. Now we can't use the same as before, right? So we have A over A of the anti-muon. Before we had A over A of the muon, but it was a different situation because we had a muon instead of the electron. Now we have an anti-muon instead of the proton. So this will be 1 over m, right? That is the relation. So the reduced mass divided by the mass of the electron, right? Because that is the case, of course, for the regular A. So in this case, we have, let's see, actually set this equal to, so 1 over me, and the reduced mass is the product of the masses, so mass of the electron, in this case, the mass of the muon or anti-muon, it's the same, mass, of course, not the same particle. Mass of the muon times mass of the electron, I guess it wasn't that bad, and then mass of the electron plus mass of the muon. But these cancel out, and we know that the mass of the muon is 207 times the mass of the electron. So down here we got 207 plus 1, which is 208 times the mass of the electron. So we get 207 divided by 208, or basically that A is equal to 207 divided by 208 times A mu. And here we find that A of the anti-muon is 208 divided by 207 times A, of course. So by plugging this in, we get a cubed, and now, since this is in the denominator, we get not 208 divided by 207, but 207 divided by 208. Cubed, of course. So now we can calculate this. This is what we already know, right? This is 5.88 times 10 to the minus 6 electron volts. And then we need to multiply by this entire thing. So by plugging all of this in, we get 1,835 times 10 to the minus 5 electron volts. So there we go. This is the result for part C. And this is basically how we do it, right? It is a relatively simple procedure. Now, the last thing that we want to mention is that the answer for part B, right, which is the part for the positronium, is quite different. Right? We got something about 4.8 something times 10 to the minus 4. It is quite different from the experimental value of 8.41. And that is, of course, because we are not really accounting for every physical thing that might happen. In the real life, a positron and an electron can't annihilate to produce a pair of photons. So, of course, the spectrum of hydrogen, or in that case, right, would end up changing. So, of course, that's why this is not all that realistic, but it's still, you know, a pretty decent approximation. So this is everything for this video. I hope that this was useful to you. If it was, please make sure to leave a like on the video, comment, and subscribe, and I'll see you in the next video. Oh, and maybe check out my Patreon. I'll see you in the next video. Thank you very much for watching.